Okay, so welcome back. So we will start the next session now, and it will be Mithun who will be continuing with the talks that he gave yesterday. Thanks. So over to you.
Right. If I'm thinking of such chemical networks, what are the generic conditions that these networks or these diffusion coefficients and so on, what generic conditions do they need to obey for me to see these patterns? Okay, so that's the aim for today. So let me start. Unless there are any questions from yesterday's part, then I'm happy to talk. So what I'll do, therefore, is we'll consider these two species, A and B, right? And let's say the concentrations of these are U and V, so, and they evolve in time, so del U, del T, and del V, del T, okay? So these concentrations change in time. These concentrations change in time inside a single cell because of the chemical reactions that are taking place. And the chemical reaction is something, whatever is that chemical reaction, I encode it in this function, f of uv for one, and then let's say g of uv for the other. Okay. So I'm not putting any constraints on what these are right now. So these are some generic chemical reactions that are taking place. And then what we'll try to see, or what we'll try to find out is what are the conditions on these functions that they will need to obey for me to have this sort of pattern formation through this diffusion-driven instabilities. Okay. So this is the chemical part, and then of course when I couple them spatially, I'll need the diffusion coefficient. So du Laplacian of u plus dv Laplacian of v. Right. For those of you from a biological background, this is nothing but, you can think of this as nothing but del 2u del x2. If you are diffusing in 2 dimensions, it would be del 2u del x2 plus del 2u del y2. If you were diffusing in 3 dimensions, there would be a del z2. So the structure of the equation stays the same. It's just that depending on the spatial dimensionality, you have these partial derivatives in all the dimensions. So this is equivalent to this Laplacian operator. So this Laplacian operator is nothing but this. So if you get confused, you can just continue to think of this one-dimensional diffusion where you have del 2u del x2, d del 2u del x2 is equal to del u del t, right? So if I did not have this reaction term, this is just my diffusion equation. Now I have this reaction term, and then we have this reaction diffusion setup. All right. So the first condition is that, what are we trying to do? We are trying to destabilize a steady state through diffusion. So that's the counterintuitive thing about Turing patterns, right? So to do that, the first condition is that you need to have a steady state in the absence of diffusion. So if things were not diffusing, you need to have a steady state. So as far as that goes, so therefore, firstly, let me look at the steady state in absence of diffusion. Steady state in absence of diffusion. Right. And therefore, I'll just write the reaction terms. So del U del T is equal to F of UV, and del V del T is G of UV, right? And I have a steady state means that, again, like we discussed yesterday, that these things do not change. So these concentrations do not change with time, which means that the steady state are just solutions of F equal to 0 and G equal to 0. Okay. So you can solve this given an given a F and a G, and let's say you find a steady state by solving. So steady state is F equal to G equal to 0, and that gives you certain concentrations. So let me call it U naught and V naught. Okay. So this is your steady state. Okay. Now this steady state needs to be stable. Again, if you remember this toy model that we did, we showed that the steady state was stable because if we think about perturbations away from the steady state, these perturbations die down with time. So similarly, we want to have this as a stable steady state, so not just a steady state, but a stable steady state. And again, the way we will look at stability is to sort of consider perturbations away from this stable steady state. So we'll consider perturbations, so let me call it U hat, which is, so did anybody ask a question? No, right. Please feel free to ask. So U hat equal to U minus U naught, and V hat equal to V minus V naught. Okay. So I'm considering perturbations away from this, right? From the steady state U naught and V naught, and I'll ask that whether these perturbations, they grow with time or they shrink with time. So in terms of these variables, or let me call it, maybe instead of hat, it's better if I call it delta U and delta V. Okay, so these are my perturbations. So in terms of these variables, you can write down these equations now in terms of those variables. So del of this perturbation, how does that grow with time? So what I'll do is, again, I'll do a Taylor series expansion, which is F of U naught V naught, right, plus U minus U naught, so that is delta U, del F del U at U naught, and again plus a delta V, del F del V at V naught, right. So this is my first order Taylor series. Whatever it is at the point that I'm expanding around, plus the change times how this function changes with respect to U, change in V, how does the function change with respect to V. Okay. And similarly for, delta V delta T is equal to G of U naught V naught plus delta U del G del U at U naught V naught plus delta V del G del V at V naught. Okay. So I'm just writing this out, this initial part. The second part, which is a little more complex, I won't write it out, but the plan will be exactly the same. So that's why I'm just taking 5 minutes to do this first part. Okay. Of course, because this is a steady state, these functions evaluated at U naught V naught are 0, right? So essentially, the equation that we have to solve is this, and again, we can write this in this nice matrix notation. We can write this in this nice matrix notation that del T of this deviations, so delta U delta V, is equal to del F del U, del F del V, del G del U, del G del V, right, times, again, this matrix itself, so del U del V. this is nothing but exactly these same equations just rewritten in a matrix form. So if you're looking at del T of delta U, that is del F del U delta U plus del F del V delta V, which is this equation. If you're looking at the rate of change of this one, then that is del G del U delta U plus del G del V delta V, which is the second equation. Okay, so just a convenient shorthand way of writing this Taylor series expansion in a matrix form. So now whether these perturbations will grow or shrink will depend on the eigenvalues of this matrix, right? So let me call this as the stability matrix. Let me call this as this matrix as the stability matrix, and let me just use this shorthand notation Fu, Fv, Gu, Gv. Right? So these are just the partial derivatives with respect to U, F with respect to U, F with respect to V, and so on. Okay. Now you can essentially, an equation of this form admits exponential solutions like e to the power of lambda t, e to the power of lambda t, where lambdas are the eigenvalues of this matrix. And then again, like we discussed in the toy problem, if the eigenvalues are negative, then it's a stable solution. If the eigenvalues are positive, then these perturbations diverge and you don't get a stable solution. Right? So what we then need to do is to find out the eigenvalues of this matrix. So, what I need to solve is this equation then, the characteristic equation minus determinant of this equal to 0, right? So that's how you have a 2 by 2 matrix. Hopefully, all of you can in principle find the eigenvalues. So this is the condition for the eigenvalues. So let me just write that out. Fu minus lambda, Gv minus lambda, minus Fv Gu is equal to 0. Right? So that means that if I'm solving for lambda, so it is lambda square minus lambda Fu plus Gv, Fu plus Gv plus Fu Gv minus Fv Gu is equal to 0. Right? So that's the equation. That's my characteristic equation. And this is just a simple quadratic equation in lambda, and therefore you can write down the roots. So lambda is minus b, so Fu plus Gv plus or minus square root of Fu minus b square Fu plus Gv minus 4 times Fu Gv minus Fv Gu. Okay, so these are my two roots. Again, this is very simple stuff, but I just so now I want these lambdas to be negative, right? Because I want my perturbations to die down with time. Okay. So if I want my eigenvalues to be negative, what are the conditions that I should have? Firstly, if you look at this equation, if Fu plus Gv is positive, I'm guaranteed to have at least one root that is always positive, right? So therefore, Fu plus Gv cannot be positive. So that is condition number 1. Okay, so let me write the conditions nicely somewhere here. That Fu plus Gv has to be negative. That immediately rules out certain types of interactions for as far as Turing patterns go, right? You cannot have, therefore, remember what is Fu, del F del U, what is Gv, del G del V. So it measures the change, Fu measures the change in F when you're changing U itself, right? So it's the auto-regulatory part of the chemical reaction. What that means is that, for example, you cannot have a network as far as Turing patterns go where A upregulates itself and B upregulates itself. Because if A upregulates itself, the mode of A you have, the mode of A you would produce, which means that this Fu would be positive, right? Similarly, if B upregulates itself, this del G del V would be positive, and therefore Fu plus Gv would be positive. Okay. So this sort of a network would not admit a Turing pattern. So this is ruled out immediately. So that's the spirit that we are trying to do. We are trying to find out conditions on these reaction kinetics that will allow Turing type patterns to form. Okay, so that's condition number 1. Now, that in itself is not sufficient. What is the other condition that we should have? We should have, so if this is negative, so that much we have said, that Fu plus Gv is negative. But now if this thing, the determinant, Fu Gv minus Fv Gu, if this was also negative, right, then negative would make a positive, right? Then this thing would admit one positive root. Is this clear? Yes? That's clear. Okay. So, therefore, the additional condition, the second condition, is that this determinant Fu Gv minus Fv Gu needs to be positive. So, Fu Gv minus Fv Gu, I hope this is not obstructing your view. Is it obstructing your view? The curtains? No, right? Okay. All right. So these are the two conditions that I find. So if your reaction kinetics obeys these two conditions, this is the trace of the matrix. These are the sum of the diagonal elements, these two. So the trace is negative and the determinant is positive. Okay. If you obey these two conditions, then you are guaranteed to have a stable steady state for your reaction kinetics in the absence of diffusion. Okay. So till now we are just looking at the chemical kinetics part, just the reaction part, not the diffusion part. All right. So then what we want to do is that we now want to say that I want to destabilize this steady state, this stable steady state, through this diffusion. Right? And therefore what we are going to do is to now look back at this equation that I have. Look back at this equation. It is this. Where I have the chemical kinetics plus I have the diffusion. And again, I now want to find the eigenvalues in the presence of this diffusion term. Okay? I found it in the absence of diffusion. Now I want to do the same thing in the presence of diffusion. And therefore, again, we'll linearize about this steady state, f of u naught v naught. And in that case, the characteristic equation is, this stability matrix A minus a d times k square, and then of course minus lambda times the identity matrix is equal to 0. Okay. So in this case, we solved stability matrix A minus lambda times the identity matrix 1 0 0 1 equal to 0. In this case, you have this diffusive contribution dk square as well. So essentially, what are we doing? Earlier, we had this, in the absence of diffusion, we had trial solutions of the form e to the power of lambda t, and we saw whether lambda was increasing or decreasing. Now, because I have a spatial component, you can think about, the most basic way is separation of variables, right? So you have a time dependent part and you have a spatial part, e to the power of ikx, let us say, right? Or ik dot r in general dimensions. And then if you, and then you take superpositions of these solutions to construct the final solution, right? So k is the allowed wave number. So it's the allowed wave vector of the perturbation that you are trying to check, and this lambda will depend on k as well then in this case. Okay. And of course, if you apply this equation, Laplacian or the second derivative on this, what you will bring down is 2 times ik. So del x of e to the power of ikx is ik e to the power of ikx. You take one more derivative, that is ik square. So this diffusion, this Laplacian acting on these solutions, on these Fourier modes, will give you a d times k square. Ik whole square is minus k square. Right? So that's what I've written down over here. Is this fine? Okay. So essentially, we are doing separation of variables. If you do the separation of variables, you decompose the spatial part into Fourier modes, you plug it back into this equation, and then you calculate the eigenvalues. Okay. Now what is this diffusion? What is this diffusion matrix that I have written? This diffusion matrix is nothing but again D in this case is just du 0 0 dv, right? Because it just comes with the why have I written v here? I don't know, u. It just comes with the u and the v term. So it's again a diagonal matrix with these two elements du and dv. Okay. Yes. Huh? We are assuming that solution, but because you're doing it on a bounded domain, a linear superposition of these plane wave solutions is guaranteed to give you a solution once you match the boundary conditions. Right? So there's no assumption here as such. I'm assuming this particular form, but I'm not placing any constraint on the solution itself. It's just a Fourier decomposition of the solution, and on a bounded domain, the Fourier decomposition is complete. So, all right. So this is what I now want to do. That I now want to find the eigenvalues of this matrix. So therefore, I want to find the eigenvalues of Fu. A is Fu minus d case d. What did I write? Du k square minus lambda. Then that is Fv. Then here I have Gu, and here I have Gv minus dv k square minus lambda equal to 0. Okay. So therefore, this, if I write out the matrix elements, this is the matrix equation that I need to solve. And again, it's exactly the same. It's just that the coefficients get a little more messy, but it's exactly a quadratic equation again. And again, you can solve for lambda, and then do exactly the same test, which is that try to find out what are the conditions for this lambda to now become positive. Okay. So what we are trying to do, we are trying to destabilize the pattern. We are trying to destabilize this stable steady state. Sorry, not destabilize the pattern. We are trying to destabilize this stable steady state. So therefore, we want conditions now for this new lambda in the presence of diffusion, to be positive. Okay. So exactly like here, we wanted the lambdas to be negative. We are now trying to find out conditions for the lambdas to be positive. Okay. So this part, I think, let me just write this out once, and then I'll skip steps because otherwise it'll take, I'll just get bogged down. But let me just write out the equation at least. Okay. So if I do this and then I arrange terms together, what you will get is an equation of this form. Lambda square plus lambda k square into 1 plus d, and I'll say what this d is. Let me just copy this out so that Fu plus, you should just work this out anyway, but let me just write from now, plus dk to the power of 4 minus gamma dfu plus gv k square plus gamma square fu gv minus fv gu. Okay, so if you write this out and you rearrange terms, you will get a new quadratic equation, which is looks a little worse than that quadratic equation we had over there, but it's essentially the same thing. And this small d here is nothing but the ratio of my diffusion coefficient. So it is dv by du. Okay. So just for simplicity. Okay. And now I want my lambdas to be positive because, like I said, we want to destabilize this. So if I want my lambdas to be positive, so lambda is minus of this quantity. Let me call it something, I don't know, j, okay, j of k square. So this is minus j of k square plus or minus square root j of k whole square, and let me call this quantity as this whole thing inside this bracket as h of k square minus 4h of k square, okay, by 2. So if I wanted to make this lambda negative, I want to make my lambda positive. So what I could do in principle is have this thing as negative. If this thing is negative, so which is this j, right, then I'm guaranteed to have at least one root that is positive, correct? So I could try to make this I should try to make this negative, all right. So, but can I make this negative? So what is, so I want this quantity to be negative, but what I have a constraint already is that fu plus gv is necessarily negative, okay, which means that this second term is positive because negative of a negative is positive. The first term is necessarily positive, k square is a positive quantity, d is just a ratio of diffusion coefficients, so it's bound to be positive. So therefore this thing I cannot make negative, okay. So this is not a route to achieve positive lambda. So therefore the only other thing that I can do is that I can play around with this term h of k square, and if I make my let me see, what do I need to do to h of k square? Anyone wants to help me out? If I wanted a positive root, h of k square should be, if I wanted a positive root, h of k square should be negative, right? Because then I will have at least one root which will be greater than this minus sign over here, and therefore I will get a positive root. Is that fine? You can think this through also. It's just a question of. So therefore, if I want my h of k squared to be negative, let me look at what terms I have. I have a k to the power of 4. That I cannot make negative. So this thing is already, this thing I know is positive. So therefore, the only thing that I am left to play with is this middle term over here. Okay? And therefore, the condition that I want in this case is that this quantity, k squared is positive. If this quantity is also positive, dfu plus gv, then I can get a negative term over here, right? So that is my condition number 3, that dfu plus gv, that is positive. That will allow your h, it's not sufficient because it still has to overcome these two terms, but at least it's a necessary condition for this h to be negative and such that you can in principle have a positive root for this lambdas. Okay? Okay. So that is condition number 3. So let's see what that means. So what does that mean? So I have one condition which is fu plus gv is less than 0. I have another condition here which says that d times fu plus gv is greater than 0. What does that mean about the relative signs of fu and gv? Anyone?
Sir,
Huh?
can you repeat what is gamma there?
Sorry, forget gamma. It is nothing. I was using a different notation in my notes.
Okay.
Okay, thank you. Let me forget gamma everywhere. Okay? So these two conditions together, what constraints do they place on fu and gv? So earlier I had said that if you have A and B, they cannot both be upregulating. So this motif was not allowed. But now that I have this new condition, this third condition number 3 along with the first condition, are any other sort of networks ruled out? for example, could I have a condition something like this, A, B, let us say both of them are repressing, auto-repressing at least, auto-inhibiting. Is this allowed? It satisfies this condition that Fu plus Gv is less than 0, right? But it will not satisfy this condition that dFu plus Gv is greater than 0, right? So therefore, this is also not allowed. In fact, if you have to satisfy these two simultaneously, what it says is that Fu and Gv necessarily must have opposite signs. One of them must be positive, the other one must be negative, right? Does not matter which is which, but you must have something like network like this. I keep keeping the, so so these are not allowed, but in principle something like this is allowed, right? Or the other way, this is repressive but this is activating, inhibited. Okay. So this is, so together therefore Fu and Gv must have opposite signs. That's one condition. If Fu and Gv have opposite signs, so what that means is that Fu Gv, the product, is less than 0 because one is positive, the other is negative. So therefore, this is less than 0, right? If this is less than 0, then what does my second condition tell me? My second condition says that this determinant has to be greater than 0, but this first term I have already said that it is negative. Therefore, this second term must also necessarily be negative. FVGU also has to be less than 0, right? So that it can overcome this part and give a positive result. So therefore, together that means that FVGU has to be negative, which means that FV and GU must also have opposite signs, right? So not only Fu and Gv must have opposite signs, but Fv and Gu must have also have opposite signs, must have opposite signs. Which means now that I have something like this, and if I say now that A activates B, then necessarily what it means is that B must repress A, right? So this is a network motif that is allowed under the conditions of Turing pattern formation to have stable patterns, or at least to destabilize this stable, homogeneous, stable, steady state that we see. Okay? So this is a possible motif that you have, or of course, you could, but that's the same thing. I suppose you could have something like this. No, I could have something like this as well, right? So you can think about, therefore, in terms of these matrices, you can think about in terms of these matrices, what sort of patterns are allowed, and I'll come to that in a second. But maybe since I showed you this simulation of Schnackenberg's kinetics, and by the way, I have, so Shakti will upload, some of you have asked me for the code to play around with. So Shakti will upload the code on the conference website along with the lecture slides. Okay, so you can play around with that code and sort of. Where is that? Okay, one thing I forgot to say that before I get to what I was showing is that so that was my condition number 3. So that tells me that this term is negative, but it's not sufficient for this term to be negative. This term also has to overcome these two other terms. So it has to be net negative. So that condition also is my 4th condition. So let me just write that down as well. So the final condition is over here. dFu plus Gv whole square minus 4d Fu Gv minus Fv Gu has to be greater than 0. Okay. So that thing has to be satisfied so that you have a net negative over here. Okay. So actually I think I have put that on the slide, so it's hopefully helpful if I can get to those slides. Here. Okay. So these are my 4 conditions for pattern formation, at least within this Turing type of a setup. And these conditions together places certain restrictions on the kinds of allowed network motifs that you are allowed to have in order to have these sort of diffusion-driven instabilities. And what does this final condition say? Essentially what this final condition says is that you will only have certain wave vectors. So, you know, I have, when I have this condition, this lambda, remember, is a function of my wave vector. So it's a lambda of k square. So what is the wavelength of the perturbation that I'm choosing to destabilize my system with? And what this says is that, you know, given a choice of this diffusion coefficients or these ratios of diffusion coefficients, not all wave vectors are going to lead to instabilities, or, you know, instabilities of all wavelengths are not going to propagate. Some wavelengths might propagate, some wavelengths might just die down. Okay? And essentially what this is showing is that if you are below, firstly what it is saying is that you need some mismatch in your diffusion coefficients. Okay, so let me just say that. If you do not have a mismatch in your diffusion coefficients, if du is equal to dv, right, if the diffusion coefficients are equal, then this first condition and third condition are directly in contradiction to one another. One says fu plus gv less than 0, the other says fu plus gv greater than 0. So you cannot have the 2 species diffusing with the same diffusion coefficient. Okay? So that's one thing to note. You must have different diffusion coefficients. That is what drives this diffusion-driven instabilities. And you need, generally if you look at these numerical solutions of these, you need to have a fair bit of difference between these diffusion coefficients before you start getting any wavelengths that are stable, any perturbations that are stable. So what this says is that beyond, below a certain critical mismatch, DC, you don't have any, none of these lambdas, none of these eigenvalues have any positive part. So therefore, all of these perturbations are going to die down. Okay. Once you hit this critical mismatch, du by dv, there is one value of the wavelength that will allow you to allow this instability to grow. And of course, then if you cross this critical value, d greater than dc, then you'll have a range of wave vectors that grow. Generally, if you waited long enough, you know, the wave vector with this highest wave vector is the one that is eventually probably going to take over the system. But to look at that, to look at how, so this, what we are doing right now, or this framework of Turing, what it says is that it says about destabilization of a previously homogeneous steady state. It does not say about stabilization of the eventual pattern, because to do that you would have to do some nonlinear analysis. So that we are not doing. We are just staying within the realms of linear stability analysis, because we are just looking to first order in delta u. If you looked at higher orders, you could do a nonlinear analysis, and that would tell you, you know, whether the patterns are stabilized or not. But generally, one just runs a numerical. Okay. Maybe I will. All right, it's fine. It doesn't matter. All right. So together, these 4 conditions tell you what do you need to destabilize, and what are the allowed wave vectors that will allow these perturbations to grow. Okay. Now, here is another sort of slightly tricky, small issue, but at least it's something to recognize, that when I say that when I draw a curve such as this, right, when I draw a curve such as this, and say that, let me just draw this curve over here. I have this lambda as a function of k square, right, and I have some value of lambda, k star, for which this eigenvalue is positive, which means that a perturbation with this wavelength or with this wave vector is going to grow. But if you're thinking about finite systems, not all wave vectors are allowed, right? Because only those wave vectors are allowed which are integral multiples of 2 pi over L, right? So you have a discretization in your allowed wave vectors, n into 2 pi over by L. So for small systems in that sense, where not all, even if these equations admit a solution, this K star might not actually be an allowed solution itself. So even though, so that is another factor to keep in mind, at least for small systems, whether the allowed wave vectors, even though you have found a solution through this sort of linear stability analysis, whether that is an allowed wave vector or not. All right. So what I showed you was simulations of these various different kinetics. What I showed you was simulation of this one kinetics, Schnackenberg kinetics, which has in a simplified reduced form this reaction. So now we are putting in forms for F and G. Till now we were working with a general F, a general G, and laid down the conditions which F and G need to satisfy. Now let's just consider one or two of these specific examples, right? And these were all examples that are built up by looking at specific sort of chemical reactions in some sense. I've forgotten Schnackenberg, I think some glycolysis reaction network is what he used to construct this kinetics. All right, so F of uv, so F of uv is some constant minus u plus u square of v, and G of uv is b minus u square of v. Right. So therefore, I can write down my stability matrix. So my stability matrix is Fu, Fv, Fv, Gu, Gv, which means for this particular case, del F del U is minus 1 plus 2 uv, del F del V is u square, right? Del G del U is minus 2 uv, and del G del V is minus u square, right? So this is what I have for the stability matrix for this Schnackenberg kinetics. Does this satisfy the motifs that we laid out over here? So this is u square. Remember, u's and v's are concentrations of these two chemicals, right? So they are positive. So u square is anyway always positive. So what I have over here is a plus, right? Minus 2 uv is negative because u and v are themselves positive. So what I have over here is let me just write the motif maybe separately down below. So this is a plus, this is a minus. That is good because we said that Fv and Gu must have opposite signs. So it does indeed have opposite signs. Here, this is a negative. This is a negative. And this thing is a positive as long as your u and v are, the product is greater than 1. So this is the sort of network structure that I have. A plus plus, a minus minus. Okay. What does that mean? Again, in terms of this, it means that what network is that? So A up change in V, so that network is something like this, and plus plus, and then a minus minus, right? So that network is something like this. Hopefully it will come back. Okay. So Fu and Gv have opposite signs, Fv and Gu have opposite signs. So provided now you choose your diffusion coefficient appropriately, you will see patterns. And indeed, like we showed, you do indeed see patterns. So this is the concentrations U and V for these two species, so for some particular choice of parameters. Okay. Similarly, you can look at another network, for example, sorry, I thought I had another, here. Here is another network which is called the Gerard-Meinhardt kinetics, which Shom Dattadi was talking about in the first day, if you remember. So again, it's built up from some underlying chemical reactions. And here, let me see. So here I have F is A minus B U plus U square by V. and G is U square minus V, U square minus V. So if I construct this stability matrix, A is minus V plus 2U by V, and then minus U square by V square, and then 2U, and then minus 1. Minus 1, right? So again, so this, therefore, this has the structure plus, minus, plus, minus. Okay. So this is this structure, plus, minus, plus, minus. Again, it satisfies all of my constraints. These two are of opposite signs. These two are of opposite signs, right? So therefore, that is something, let me see. So that is like upregulates itself, that is a plus, and then B also upregulates that. So that is the second plus, and therefore these two have to be the repressors. So, right. So this is the network structure corresponding to the Schnackenberg. This is the network structure corresponding to the Gerard-Meinhardt. Okay. So you can try to sort of think as to what sort of motifs are going to be allowed. So here are these motifs. So this is, for example, the Gerard-Meinhardt. This plus plus minus minus is like the Schnackenberg kinetics. Okay. So you can try to convince yourself that these, in fact, are the only possibilities that you have in order to have a pattern formation under this Turing sort of a framework. Okay. So given a chemical reaction, then if you're thinking about whether this will form this sort of diffusion-driven instabilities, and therefore will form patterns, if you can write down the chemical kinetics corresponding to whatever gene networks that you're looking at or you're interested in, and it follows these, it follows any of these patterns, then in principle it might admit a Turing sort of instability. If it doesn't, it's not to say that it will not form patterns. It will not form patterns through this mechanism. There are, of course, other mechanisms to form patterns, lateral inhibition, and so on and so forth. But at least it will not have this Turing type of instabilities. All right. So this is the other thing that I was saying. I think, yeah, I have some 5 minutes or so. The other thing that I was saying is that if you have small systems, so for example, here is Schnackenberg kinetics. So okay, so this is just the Schnackenberg equations in 1D. And here one has simulated up to a length 3. Okay, so this is a domain of size 3. And you see that in this domain, when your domain length is 3, there is no destabilization of the steady state. You still have this uniform concentration throughout. Okay, this is just one of the species, let's say U. Okay. On the other hand, if you now increase your length to 4, you now start getting these sort of instabilities, these heterogeneities that appear. So you have now destabilized the steady state once you have increased your length. And why is that? Because now in the earlier case when L was 3, there was no wave vector so the same parameters for both of these figures. So there was no wave vector that was allowed and had this positive eigenvalue. But in the second case, there is some wave vector, and you get some sort of a characteristic length scale that will appear for these perturbations. The other thing, therefore, you can think of that if there is some length control. So this is another example actually. So before I move on, this is the same example, but in 2D. So in 2D, I showed you the spot patterns, right? Yes. I'll have to check. I think these are no flux boundary conditions. Okay. I'll just check the code once more, but I think these are no flux boundary conditions. And looks fairly flat at the boundaries. So del C del X is probably 0. Right. All right. So now this is an example in a 2D system. So in 2D system, I showed you these spot patterns, right, from Schnackenberg kinetics. It's still Schnackenberg kinetics, but now I consider two 2D domains, one which has this square form and the other which has this rectangular form. Okay. And again, simply by varying these ratios of the lengths, the L1 and L2 of the domain that you're interested in, you can change the type of pattern that you get. So again, in both in this figure and in this figure, The parameters are the same. Only thing that has changed is the ratios of these lengths, the length of the system. So here it is like a square, here it's like a rectangle. And this, by changing the geometry of your system, you can change the type of pattern that you get. So for example, the circular patterns. Red हो गया battery. But I can keep talking. So this particular simulation is for apical growth, where you have this domain of length L, and this one tip is sort of growing with a velocity v. So it's growing linearly with time with a velocity v, v being the slope of this line. All right, so let me just wrap up. And so therefore, what I want you to think about, so we have this, of course, general framework of Turing type of patterns. But these Turing patterns, demand certain conditions. Of course, they demand all of these conditions. But even beyond that, in some sense, what it demands is that if you go and simulate these systems, what it demands is that this mismatch between the diffusion coefficients, this small d factor over here, that, like I was saying, generally needs to be quite large. Okay. Now this presents a sort of a problem, because when we are thinking of diffusion of chemical components or morphogens or proteins and so on, roughly the diffusion coefficients are not that different. They might be 5-fold, 10-fold, but they're not generally not going to be 100-fold. Okay. So this mismatch, and often you'll see when you're simulating these sort of Turing patterns, in order to have these eigenvalues which are positive, you do need a large mismatch in the diffusion coefficients. So then one has to think about, how does one achieve these sort of, how do you achieve these sort of mismatch in diffusion coefficients if the intrinsic diffusion coefficients are not that different? And there can be different ways. For example, often when you have morphogens diffusing, like we're thinking about bicoid. This is not a model for bicoid, but just to give you an example, since we've been talking about bicoid for so long, bicoid gets trapped inside the nuclei, right? So if you have morphogens, or if you have signaling molecules that get trapped either because of some structure, or maybe they get bound to the membrane, then if they spend a fraction of time in the inactive state where it's not moving, then if you calculate the effective diffusion coefficient, that can be pretty small. So even though if I have some species that is diffusing, and it can exist in the free state, or it can exist in a bound state, let us say, even if this bare diffusion coefficient d is large, depending on this kinetics, how long it stays bound and how long it stays free, you can end up with an effective diffusion coefficient, which is fairly small, for example. So there are ways, especially in these developing systems, in which even though the intrinsic diffusion coefficient is not large, intrinsic diffusion coefficient does not have a large mismatch, effective diffusion coefficients you can generate a large mismatch through interactions with other components of your system. That brings to this sort of an issue about increasing the complexity or the number of components. So for we just worked it out for a 2-species system, but there could be another species. There could be a 3-species system. There could be a 4-species system. We have seen all over the last 2 days these complex gene regulatory networks. It's not just two types of chemicals that are interacting with one another. In principle, you can have many. And if you have more than 2 components, you can again, the calculation becomes much more difficult. But you can again work this out and try to see what are the conditions for pattern formation in such a case. And interestingly, for example, in a 3-component system, for example, just to show how these two tie together, in a 3-node sort of a system, people have shown that if you introduce one more component, you do not need very large mismatches in the diffusion coefficient of 2 of the components. Okay, so you can get by even without large. So this is another way to skirt that requirement of large mismatches, is by having more components, and that might allow you some more flexibility in the parameter space in order to generate these patterns. Then, of course, I talked about patterns in growing systems, which is especially important for development. So you can think about different types of growth morphologies, and then how patterns change in these sort of morphologies. And finally, the thing that another thing to sort of keep in mind is that how robust are these patterns. So if I change parameters, so I have all of these parameters over here. If I change the parameters of my model, A, B, something, do I still continue to get patterns? So how robust are these patterns with respect to variations in parameters? But you could also possibly think, how robust are these patterns with respect to the network motifs themselves. So if I have these nodes and edges of these interacting species, and I change maybe the weights, or I take away one node, or does that completely destabilize the pattern? So these stability issues and the robustness issues are also worth thinking about in these sort of systems. So I leave you with these sort of thoughts. In general, this is a very broad framework for generating patterns, and at least in chemical systems, people have explicitly shown Turing type of instabilities. Even in developmental systems, people think that they do play a role. Okay, so I'll stop here.
Okay. Any questions?
In your one of your slides, you have shown the different kind of
Which one?
yeah, that one. Sign structure. So what these subscripts are for? The P and C.
These are just two types of stability matrices, or patterns of interaction between the A. I have forgotten. Are you asking what the P stands for and what the C stands for? I have to check. I have forgotten what this stands for. It's just, I think. Let me try to see. Let me try to recall. Yeah, I don't recall. I'll have to check and. But essentially, it just tells you what sort of motifs are allowed within the constraints of these sort of Turing type of instabilities. Yes.
So the wave vector that we actually see in a Turing pattern, does it some way connect to the wave vector that you get from the dispersion relation from the by linearizing the system?
Yeah. So essentially, of course there is no way of proving this within the framework of linear stability analysis, but it is essentially this wave vector that has the largest eigenvalue that dominates in long times. So this is the one that will produce the characteristic length scale.
So at a longer term, like the patterns that we will see, so the wave vector in that case would match with this wave vector.
So you can, yes, but you can try this in a simulation sort of a framework. So you know what is the wave vector, for example, from this sort of an analysis.
Yeah.
Then if you simulate and look at long times and see what is the length scale that is emerging, it is generally going to be this wave vector that is emerging.
But that is interesting because at longer term, the non-linearity will come
Exactly.
into the
So
play,
I,
right?
I,
So,
I
but-
cannot
but-
generally, there is no proof, and in principle, depending on what sort of a term you introduce in your actual kinetics, you could in principle have other things, but generally it's this wave vector with the largest eigenvalue that will probably set up the characteristic length scale. But it's you can check that in simulations and see how that matches up.
Thank you.
So Mithun, this is about that growing domain thing that you showed. So I remember Shakti and I once were trying to do this. The problem was like, how to implement the initial condition for the, like a cell basically we were arguing that, we can think of it as a row of cells and then the cells divide and after a certain time and then they divide and so on.
Correct.
The question was how do we, ascribe the initial conditions of the daughter cells? So is it like you just divide the whole material into half the concentration or you do something else?
So I'll have to, so that is different from this growth, because this growth is, like I was saying, an apical growth. What you're saying is essentially like exponential growth essentially, where every daughter cell is dividing into two and, every mother cell is dividing into two daughter cells. So I've never done that simulation, but in principle, for example, this Miney's paper has this exact simulation of this sort of a growth as well. So I can check and see what sort of a condition they take. Miney has this very nice review on these sort of systems with growing domains as well.
So any further questions? Okay. So if not, we'll thank the speaker once again.
Thank you. Thank you.
So just to make a quick announcement, so we have been uploading